First of all, thank you to the organisers for putting on this absolutely fabulous conference already and for giving me the chance to talk here. Yes, that's the one joke in the talk. Everything is dead serious now. So the thing I want to talk about, the objects I'm interested in are these things called multiple polylogarithms. And so just to go straight off with the definition, they are these say, nested sums, some functions of many complex variables, x1 through to xt, that are defined on some polydisk. It's something that looks kind of like the summand you put in to say the Riemann zeta function, or maybe the Taylor series for log 1 minus x. The idea is these things are some generalization to many variables and to some higher notion of, well, some notion of highness of the logarithm function, the one we all know and love. So logarithm minus log 1 minus x is giving us the first polylogarithm, say just polylogarithm there because it's one variable, and these one variable things tend to be called the classical polylogs. Then if you add more variables, you get the multiple polylogs. But the idea is it sort of occurs as some function that you get by repeatedly integrating things like this. I'll explain this a bit more carefully later. But associated to this, we have a few useful concepts. I've already vaguely said some notion of highness here. By the highness, I mean the weight of the function. That's just given by summing up all of the indices. So Li1 has one index that's 1, so it's weight 1. It also has one index, so d is 1. It has depth 1. But you can have functions with any sort of indices you want as long as they're positive integers. And you can have something really high depth, really high weight. The topic that, the idea I'm thinking about with this is trying to understand what the depth filtration on these objects is like, to understand the properties and structure of that. So I'll give you some examples in the next slide, but roughly this notion of depth is, in a sense, a bit artificial. It's like it's something coming from the way we're writing this series out, and it's not quite as intrinsic as you would like. There's a question.
I don't know if you already answered this, but the M1 through M2, are those just ranging over all the positive integers?
Yeah. So this is a sum over all positive integers. M1 goes from 1 to infinity, M2 goes from M1 plus 1 to infinity, and so on and so on.
What should I think for a filter? Linear combination or some algebra generated by the user?
So the filtration is take all the polylogs, take the space, the Q vector space, maybe C vector space spanned by all things of depth less than or equal to some fixed thing. And so the interesting thing is we can relate functions of different depths. It might not be obvious to start with, but I mean, this is a relatively silly example once you see how it works. The idea is if you take the product of Li1 and Li1 and just write out this sum, it's a sum over, I should use the pointer, shouldn't I? It's a sum over m is 1 to infinity, L is 1 to infinity. Well, we can split it up into a bit where m is less than L, m is greater than m is greater than L, and m equals L, and then just commute the variables around so this thing makes sense, and we get exactly the terms up here. So depth is a bit of a strange thing here because we can have relations between things of different depths. What we expect is things of different weights don't have any relations, but things of different depths can have relations. And this is actually just a general phenomenon. It's coming from so-called Stuffle product. So this is not too different to the shuffle product we saw in Rose's talk yesterday, except that instead of, when you take your deck of cards, I don't have one to hand, you take your deck of cards, shuffle them together, and then this time we can take two things and two cards and sort of glue them together and, I don't know, cheat in a bad way at poker or something. But the more surprising thing is, okay, this was like an artificial example. We've taken something of depth 2 and depth 1 and written it in terms of depth 2. It's more interesting when this goes the other way. You take a function that looks like it should be, depth 2 depending on 2 variables. There's no good reason why you should be able to write it in terms of these things with 1 variable, but you can. There's an example. And I'm saying here this is a power series identity, so it's something you can give, I don't know, the analysis 1 students or something, a little exercise to prove this. There's like at least 3 different ways to prove it, so and they're all quite straightforward. You either differentiate and just check that the difference is constant and see that the constant has to be 0 in either one of the variables, or you can do it as a combinatorial thing by looking at what the coefficients of x to the n, y to the m are here and what they are on the other side. So this lets us reduce a function of depth 2 to depth 1. You can actually do something similar for a function of depth 3. So I've written it out explicitly here just for, just to actually give you an explicit concrete formula. I'm cutting a few corners as well, because I'm saying under here there's a load of product terms. You can fill them in if you want. There are sort of techniques to do that. But the reason I'm going to work modulo products for most of the rest of the talk just because the identities are a bit simpler. Unfortunately, this does mean that I'm also ignoring things like 2 pi I times products of logarithms or dialogues and things like that, which unfortunately means maybe I'm the person who's had to quotient out by 2i pi and get rid of that from spec q bar, so maybe I should go. But yeah, you can really just think of this right-hand side as being simpler stuff. It's all depth 1 functions where you've plugged in some rational argument. Rational functions are nice, depth 1 stuff is simple, and then we have a way of writing this complicated depth 3 thing purely in terms of depth 1, so it's nice. So then the obvious question you want to ask is, does the same thing work in depth 4? Maybe all of the multiple polylogs are really just a complicated combination of depth 1 things. But no, I mean, the sort of tongue-in-cheek answer, the reason why this doesn't work is because 4 is 2 plus 2. It'll clarify exactly what happens there in a few slides. But yeah, the answer is apparently you can't reduce even this depth 2 function in weight 4, this Lie 3, 1, to depth 1 things, but you can instead reduce some interesting combination of it. So these 2 terms, this Lie 3, 1 of 1 minus x over y, comma y, and x over y, comma y, again comes to a combination of depth 1 things. So the question we want to ask is, how can we understand and predict these sort of reductions, so reductions as in the first proposition, and how we can predict the sort of obstructions that mean we only get results like the second one, where you get these identities that cancel. But before I go into answering some of the details about that, I at least want to try to make some connections to at least 1 or 2 other talks that have appeared here. So we heard in one of the lightning talks about this Dedekind zeta function of a number field to sum over all of the non-zero ideals in the ring of integers. You take the norm of the ideal to the minus s. We also heard that the analytic class number formula tells you something about the residue of this function at 1, and that it's expressed in terms of a regulator. What wasn't said in the talk is that the regulator is some combination of logs of units of the number field, or I'm going to reinterpret that as Lie 1s of units of the number field. And now we have a sort of suspicious 1 floating around here and floating around here. What happens if we make them 2? Does something work? And what happens if we make it 3, and so on? Well, there's a conjecture that the values of the Dedekind zeta at some positive integer n can be expressed by the classical, the depth 1 polylog of index n. And there's some connection to higher units in K-theory. I'm not going to make that precise. But there is some way of relating this Dedekind zeta function to some really high depth object called a Grassmannian polylogarithm. So it's actually something that's defined on like configurations of hyperplanes, so it's Grassmannian in that sense. And then the question is, can we reduce this thing to depth 1 somehow? And if we can do that, then at least this part of the conjecture showing zeta f of n is expressed via classical polylogs. You know, there's a road to proving that. There's also some connections to areas like hyperbolic geometry. I don't think this was mentioned by anyone in the conference, unless I've been very negligent. But there's also connections to cluster algebras, we heard about on Thursday. And I'm sort of obligated to say there's some high energy physics connections as well. You know, it's useful for grant applications and things. Is that? So now I wanted to make a little bit more precise this route to finding what the obstruction is and how to predict these formulas. So actually, I wanted to recall this notion of an iterated integral that appeared in Rose's talk on Thursday. It's maybe a special case of it, but it's effectively the same thing. We're taking very particular differential forms, dt over t minus x, and you give them all the indices you need to make this an integral with the right depth. And by expanding each of these things out as a geometric series, you can show that the polylog with index k1 kd of x1 xd is some iterated integral, where here, just for notational simplicity, I've tried to group all of the variables together into some capital X. The capital X's are products of consecutive X's, just to make, they get plugged in here, just comes about by the iterated integral procedure. Now, this is a good starting point, but actually we want to lift these things to some notion of a motivic integral. There's some purely algebraically defined version of them that has better properties. I mean, the sort of technical words to throw around is that Goncharov lifted these things up to be periods of framed mixed Tate motives to define some motivic iterated integral. Maybe the down-to-earth way of thinking about it is, instead of taking the thing you're integrating, the region you're integrating over, and doing the integral, you want to keep track separately of, I have these differential forms, I'm integrating these against some integration chain. So it's coming about as like a comparison isomorphism between Betti homology of something and Durham cohomology of something. But basically, you're just keeping, on a down-to-earth level, you keep track separately of what you're integrating and what you're integrating it over. And then this gives the objects much nicer properties. They now, as I say, form a weight-graded Hopf algebra. So in this setting, there is a notion of weight that gives you a grading. That means things of different weights can't be related at all. That's the expectation we have. And here it's true. And of course, from the iterated integral definition here that's relating the classical polylog and iterated integral, well, you just make both sides motivic and you define a motivic polylog. Now, to use this to see why some of these identities hold and what these obstructions are, I do need to make use of the co-product. Well, actually, I want to, again, work modulo products everywhere just because it's a bit simpler. So actually, I'm working in the Lie co-algebra. Do I have to call that queer L?
Yes.
Good, okay, queer L. And in this setting, there's a very explicit combinatorial formula for the co-product. And so this is probably really sloppy notation, but just from co-authors and collaborators, we tend to write, you should write it as a little delta to be the co-bracket in the Lie co-algebra, but it's coming from the co-product in the Hopf algebra, and there's no confusion, so I'll stick with actual delta here. So it's a combinatorial formula that tells you to take your iterated integral with whatever these indices are and chop out a sequence from xi to xj, put it on one side of the wedge, and get rid of the interior bit of that and put it on the other side of the wedge. So note that xi, xj are appearing on both sides. And there's a sort of pictorial mnemonic that always gets shown in these cases. It's better suited really to the co-product in the Hopf algebra, because in the Lie co-algebra it simplifies a bit too much. But it's just the mnemonic is you put these variables that are describing the integral around a semicircle, and then you're drawing all possible segments and cutting off some top piece that goes on one side of the wedge and some main polygon bit that goes on the other side of the wedge. And then in the co-product, there's actually, you're taking lots of different segments out and doing it in all possible ways. Now, the depth filtration that kind of didn't quite precisely define, but explained verbally, actually behaves quite nicely with this co-product. So if you take something of depth less than or equal to d and take the co-product of it, well, you get a piece that is still depth d, but it's wedged with something of weight 1. And then you have a bunch of other stuff that's depth less than d, wedge depth less than d, in a way that the total depth is what you started with.
Okay, I think some of this was fast for me. Could you explain some symbols on this slide?
Which symbol should I start with?
Start with F.
Oh, so here F is just a number field. So really these integrals are, the indices are taken from some number field. If it helps just forget that there's an F there, think of it as just some indeterminate variable everywhere. But to be a bit more formal, you need it to be in some number field.
And then L of F.
L of F is then just the polylogs with value, with these indices taken from the number field F, and we view them mod products. So
It's symbolic. You're not literally taking values of the x's. That is sort of, maybe they're taken as formal power series?
no, in this case, it's the motivic version, so it's this purely algebraic construction. You have some differential form that's describing the integral that describes the polylog, and you have some integration chain that describes the integral that describes the polylog. But you can think of it as just a purely formal symbol here. So formal symbol Li n1, k1, k2, of x1, x2, motivically, and this is viewed mod products. And I've got some more concrete examples of this on the next slide. So it might be helpful just to go straight there. The only thing I was going to say more on this slide is the reason why this works, but it's just to do with how the segment you're cutting out. If you don't remove something that's non-zero, then you just have an integral that is really a product, and so you can ignore it in this setup. It's not so important to understand why that works. I'd probably go straight on to an example. So if you do this construction and look at the coproduct of Li4 of x, or this formal symbol that is representing this analytic function on the low down level that is Li4 of x, then the coproduct of it, you do this computation, doing the semicircle, cutting out segments, and you find that the coproduct of Li4 of x looks like log of x wedge Li3 of x. And actually, this isn't too different from looking at the derivative of this as an analytic function. If you write down the analytic function Li4 of x and look at its derivative, this is more or less what it is. You can just do the term-by-term differentiation in the series. When you start looking at the coproducts of higher depth things, they get a bit messier, but all of this is just coming purely from the combinatorics of this cut out segments from a polygon construction, and there's maybe a couple of identities I've used to simplify and rewrite things, but it's purely combinatorial at this stage. And the thing I wanted to point out here is, well, the Li4 stuff has a component that's log, so is weight 1, wedge something that's weight n minus 1. All of the Li4 stuff looks like that. And then if you change the variable x to some rational function, you just get the same there and there. They all live in this L1 wedge L3 space, the weight 1 wedge weight 3 stuff. And that's exactly where the first two lines of the depth 2 coproduct live. So we can sort of pretend we understand them reasonably well. We can imagine that maybe they all come from something that's really a Li4. The stuff on the third line is now the interesting new stuff for the polylog. So it looks like Li2 wedge Li2. It's a weight 2 thing, wedge a weight 2 thing. And so this is somehow telling us that the depth 2 polylog Li3.1 is really not at all related to depth 1 things. Because if we just ignore anything that's weight 1 in this setup, and I'll write the coproduct with a bar over it to mean that, then this reduced coproduct, that's what I call this, that's what one calls this thing. The reduced coproduct of Li4 is just 0, it vanishes completely. But the reduced coproduct of Li3.1 is non-zero. So there's no possible way you can get Li3.1 by adding together a bunch of Li4s. And that's exactly why we had the obstruction in the first few slides of the introduction. The question you want to ask now is that the only obstruction that you get to this thing? Like if you can find some combination of Li4s, some combination of these depth 2 things where there's no weight 2 wedge weight 2 piece, does that guarantee you came from this depth 1 polylog? And the conjecture, which is actually in this case now settled, but the conjecture is, in this case in weight 4, is that that's the only obstruction. More generally, the conjecture would be, if you take any weight polylog of any depth and compute this coproduct, as long as it lands purely in the weight 1 wedge, whatever the complementary weight is piece, as long as it lands completely there, it's classical depth 1 polylog. If there's any contributions that are in higher weight wedge, higher weight piece, that's the obstruction. And that is exactly what I meant by the weight 4 polylogs can't be reduced because 2 plus 2 is 4. There's a new piece where it can land that prevents you from being reducible to depth 1. And so then you try to understand what happens in some small weights with this type of obstruction and how it relates to the conjecture. So we can look at what happens in weight 2 and in weight 3. We look at the reduced coproduct there. There is just no space for anything like weight 2 piece wedge weight 2 piece. So everything has to land in weight 1 wedge, the complementary stuff. The reduced coproduct of any polylog there is 0. And so that means, we have to have, or we expect to have, Li11 is sum of Li2s, Li311 is a sum of Li3s, and that's what I had in the introduction. So it looks good so far. And then if you do some tweak of the variables to what I wrote for the coproduct of this Li3.1 thing, I can just get a slightly cleaner expression that looks like Li2 of x wedge Li2 of y. And now you can ask, well, can I find some way of combining a bunch of different Li2s of x so they all cancel out? This is like a so-called functional equation for Li2. And there are indeed plenty of those. This is a sort of property of polylogs that holds generally, that there should be some non-trivial functional equations. This is all generalizing the fact that log of x times y is log of x plus log of y. This sort of property just keeps propagating upwards as far as we can tell. And so there are sort of some basic symmetries that, again, you can fill in what the product terms here are and write this as like a power series identity or something more concrete or down to earth. But you have these two symmetries relating Li2 of x and Li2 of 1 minus x, or Li2 of x and Li2 of 1 over x. And the identity I gave in the introduction in weight 4 is essentially the reduction that you get from plugging in one of these. So that's also true. In weight 4, the more complicated thing to find is when we plug in the so-called generic functional equation for Li2. So there's something called the 5-term relation. And I'll just write it down like that for the moment. I was going to make some connection here that this is coming from, or can be interpreted as something in hyperbolic geometry, that Li2 tells you about a volume of an ideal hyperbolic simplex, and this is counting sort of signed volume of a collection of 5 of them that cancel out. But the way I want to do it is to go back to the cluster algebra talk on Thursday, I've shamelessly stolen the slide here, and there's actually, does that count as, okay, good. We saw that there were 5 different variables here, x1, x2, x3, x4, x5, and they can all be written somehow in terms of x1 and x2. Well, there's some cluster algebra magic that means that from any sort of construction in a cluster algebra like this, where you loop round and come back to yourself, you get a functional equation for the dialogue. I don't quite have enough time to explain exactly why, but there's a connection to cluster algebras here. You get functional equations for these polylogs somehow from cluster algebras. And there's some idea of trying to understand more generally how things like this arise. But, yeah, but of course.
The variable x is supposed to be, the variable x is supposed to be less than 1 in absolute value. This is more relevant to the previous slide.
Oh, no, sure.
Now you're adding 2 power series where this can't be true at the same time.
No, that's definitely true. There is a notion of analytic continuation that you get from the iterated integral expression. So you can take your series that is defined for the variables being less than 1 and continue them out into the complex plane.
For the ordinary logarithm, this is multi-component.
Indeed, but that's why I want to work modulo products. So all of these, the 2i pi factors that are coming from looping around and getting an extra log times 2 pi I can ignore them. So modulo products, the multivaluedness doesn't play a role.
So your identity from the previous slide, it holds kind of like modulo products in the same way, and the symmetry is important.
So in that line, yeah, you can fit this. You can fill this out into some statement that is true for analytic multi-valued functions if you choose branch cuts correctly. But
presumably your upper L, which is still a little magical to me, is kind of taking care of this.
More or less, yeah. It means that the factor like log x times log 1 minus x that appears somewhere on this side, I don't need to care about it. It just makes it a bit easier to work with.
Is superscript differentiation for image in that quotient, or is it actually?
It's more or less the image of this motivic polylog in that quotient, yeah. So I'll just say here that for this 5-term relation, you can also write down and find, again, in this modulo product setting, some increasingly complicated series of terms on this side where you're plugging in rational functions. This is something you really don't want to see in full, but you can find it explicitly. And you then get that Lie3-1 of 5-term relation, suitably tweaked, does reduce.
How many terms are in this line?
122 plus epsilon. There's some change to what, and you're going back and forth to what was actually found. There's some tweaks you do. It gets complicated. That's why I do want to ignore products to make it a bit simpler and then ignore things a bit further.
Well, the epsilon means
So,
things you'd rather ignore.
well, no, the epsilon here is just because compared to the original way this was written down, there might be some extra conversion thing you have to add. There's a couple of terms extra. The real issue is there's 122 of them that. So, I mean, originally this was found with like computer algebra and lots of experimentation. It's since been understood more conceptually, so that you can derive this thing without finding explicit terms. Now, the thing I kind of wanted to build up to is that you can start to understand higher depth polylogs in a similar way, coming from iterating this coproduct. You can understand the depth 3 things by picking out what should be genuinely depth 2 terms here. And you can again show similar things so that the genuinely depth 3 function has a contribution that looks like Lie2 wedge Lie2 times Lie2 times Lie2, which means it can't be written as depth 2. And maybe this is a good place to end. there is a conjecture that this is exactly the obstruction that tells you what the depth of the polylog should be. You can take this coproduct and sort of iterate it several times to pick out what's genuinely the highest depth bit here, and then what's the highest depth bit in the next slice, and so on, to see what depth your function actually should be.